Fourier series. And we will first work with function of 2 pi period. Function, let me say f here, a function of 2 pi period. So not necessary that 2 pi is the smallest period. We can work with any function f which has period 2 pi. Example 1 is a function. So like f of t equal to 1 is a function of 2 pi periods. In fact, for any constant function, you can choose any positive real numbers to be the periods of this function. So this is an example of functions of 2 pi periods. Cosine of say mt is a function of 2 pi periods. Sine of mt is also a function of 2 pi periods. So these we know they are of 2 pi periods, and we will build any other function of 2 pi periods based on those functions. So think of those functions, they together 1 cosine mt, sine mt, they will form a say basics. You can build any other function of 2 pi periods. So Fourier proved the following. Fourier shows that you can actually express any function of 2 pi periods. So any function of 2 pi periods, and not necessary to be continuous, and it can be piecewise continuous. F here can be piecewise continuous. Piecewise continuous function of 2 pi periods, then ft can be written as a0 divided by 2 plus the sum m from 1 to infinity am cosine mt plus bm sine mt. This is the Fourier series, and we want to compute, so given a function f, piecewise continuous function f of 2 pi period, we want to compute all those coefficients a0, a1, a2, am, b1, b2, bm. These functions here, they are piecewise orthogonal, and each of length square root of pi, except this one has length square root of 2 pi. So I will write down the formula for that, but all you need to remember is that they are piecewise orthogonal. Each of length square root of pi for m greater than or equal to 1, except 1 has length square root of 2 pi. So let us write down the formula for these properties. They are piecewise orthogonal. This means that if I do the multiplication, say the dot products or the inner products between any of two functions of those, then they will be 0. So that is inner products we know, and these products we use is from minus pi to pi. Say the first function g1, the second function g2 dt. This one will be our inner products. For convention, we will use the interval from minus pi to pi. So now let's do this. They are piecewise orthogonal. If I take the products between 1 and cosine of mt, for any m greater than or equal to 1, I take this pair, the product of this pair, dt, this one will be 0 for any m greater than or equal to 1. You can do computation to verify that. You also have, if I take interval minus pi to pi 1 and sine mt dt. I also have 0. So 1 is perpendicular to sine. So 1 is orthogonal to cosine. 1 is orthogonal to sine. Cosine is orthogonal to sine. Integral minus pi to pi cosine mt, and I do sine nt dt. This one will be 0. So the function cosine mt and sine mt are orthogonal. And now I can also do the products between cosine and cosine. We have cosine mt and cosine nt dt from minus pi to pi. We also get 0 if they are two different functions. So if m is different from n, and we get the length if they are equal, m equal to n, m equal to n. This one is actually cosine nt. Do the inner products with cosine nt, which gives us the length of this function square. And as we talked before, the length, you think of that as the length square root of pi. This one will give us square root by square pi. So that is one easier way to remember all those formulas without needing to compute that all again. You can all verify these ones by doing computation. You have similar result if you do integral sine mt sine nt dt. And this one equal to 0 if m is different from n, equal to pi if m equal to n. And the last thing is about, I claim that one has length square root of 2 pi, and this is minus pi to pi. 1 inner product is 1, still 1 dt. This one is easy to compute that, and if you do the computation, you see that this is t from minus pi to pi, which is pi minus minus pi, which is 2 pi. So that's why the length of one square gives us 2 pi. Therefore, that length as claimed here is root 2 pi. So we don't need to do those computation again. Just remember this. These sets are pairwise orthogonal. H of this cosine and sine has length square root of pi, 1. For 1, you don't need to even remember that. You can do computation again to see that this integral 2 pi. Now, using all of these formula right here, we can compute the coefficients a0, am, bm for a given function ft. So let's compute that. For this function ft, if we want to compute, say we want to compute a0 first, we will integrate both sides of this equation from minus pi to pi ft dt. So integrate the right hand side, I have minus pi to pi of the right hand side dt. Now they are all summed. I can separate that term by terms. a0 over 2, just a number, take it out, minus pi to pi dt. That is our first term right here. For the second terms, the sum, I take it out, m 1 to infinity, am minus pi to pi cosine mt dt. That is all the term for cosine. And you do the same for the last term. So this is summed upon Bn sine mt. The sum m from 1 to infinity is Bm minus pi to pi sine mt dt. Now these terms will give us 2 pi as we just computed. So this one a0 over 2, a0 over 2 times 2 pi. These terms, as we said, this one will be 0. So this one is just the inner product between 1 and cosine mt. We wrote the formula right here. This integral 0 for any m greater than or equal to 1. These terms will give us 0. Similarly, these terms will also give us 0. So everything else 0 except the first term. So plus 0 plus 0. Therefore, the right hand side is pi a0. So 2 and 2 cancel out. Your integral of ft dt equal to this. So given any ft, you can compute these terms divided by pi, you get a0. a0 1 over pi integral minus pi to pi ft dt. So this is our first coefficient. Now we have am and bm to compute. To compute am, you multiply cosine nt to both sides and you do integrating both sides. Here's our equality. Now I want to multiply cosine mt both sides. ft times cosine nt. So the right hand side multiplies cosine nt. This one gives us a0 over 2 cosine nt. The sum here, I can just do distributive properties. This one m from 1 to infinity am cosine mt cosine nt. So I multiply this to this term and do the same for the second one. And this is all summed from m greater than or equal to 1. M from 1 to infinity bm sine mt cosine nt. These terms equal to cosine nt times ft. Now we can do integrating both sides. Integral minus pi to pi ft cosine nt dt. Integral minus pi to pi. First term here. So for the first term, a0 over 2, just a number, I take it out. Cosine nt dt plus, so I do integral terms by terms. M from 1 to infinity am just a number, doesn't depend on t here, so I can take it out of the integral. Minus pi to pi cosine mt cosine nt dt. So for this, all these terms, the sum m greater than or equal to 1. Similar for the last terms. So that is I do the integral here. So this one doesn't depend on t. So we'll take it out of the integral. Minus pi to pi. This is what we get after integrating both sides here. And now look at this. The first term's 0. As we said, this one you can think of the inner products between 1 and cosine nt. This one is 0. This one you can think of the inner products between cosine and cosine. If you have m different from n, they are pairwise orthogonal. This one gives us 0. If m equal to n, this one gives us the length of cosine nt square. That's the only case is not 0. And the length of cosine nt square will be pi. So this formula right here. So equal to 0 if m different from n, equal to pi if m equal to n. And for the last terms, this one will always be 0 because sine and cosine, they are orthogonal. Sine and cosine, they are orthogonal here. So integral here, 0. So these terms always 0. 0 plus only one term non-zero here. 0 plus a term that is non-zero when m equal to n. A, let's say an, because I use n here for the left, so I keep an. So integral, or let's do it slow, minus pi to pi cosine square nt dt plus 0, because the rest they are all pairwise orthogonal. This one is pi. An times pi. So an will be this term divided by pi. An equal to 1 over pi multiplies this integral. So now, for given function ft, you can compute the coefficient an here. So that we compute all of this coefficient of cosine. Similarly, we want to compute the coefficient of sine. What we do is that we multiply sine of nt to both sides of this equation. You take the integral, both sides, you get all the term will be 0, except that one term when you have m equal to n. And I say similarly, you will get bn 1 over pi minus pi to pi ft. Now we multiply sine nt dt. That one will give us a formula for all the coefficient here. So we computed all a0, am, bm. So here is our formula for the Fourier series of function ft. Ft is a piecewise continuous function of period 2 pi.